Hi everyone! Today we'll be going over Chapter 3 of General Chemistry for the MCAT, which covers bonding and chemical interactions. Chapter 3.1 is about bonding, and it starts off by talking about the Octet Rule, which I like to think about more as the Octet Suggestion, because there are many different instances where the Octet Rule doesn't work perfectly. But in general, the Octet Rule is a good way of remembering that elements like to be in their noble gas configurations, because this is the most stable. And if you don't know about this topic in depth, you can watch my last video, which talks about the Octet Rule and noble gas configuration a lot more in depth. So in general, elements like to have 8 electrons in their valence shell, and this can compose of both electrons that belong completely to it and electrons that are shared with other atoms in bonding scenarios. So some very notable exceptions to the Octet Rule are helium, hydrogen, and lithium, which are happy with just 2 electrons in their valence shell. And this is because helium and hydrogen are in the first period, which means that they're happiest when only their one s orbital is filled, because hydrogen's nearest noble gas is helium. And lithium is similar in that it's very hard for lithium to reach the neon configuration, because you would have to add 7 entire electrons to it. So lithium is happiest in its helium configuration, which only has 2 valence electrons. The next exception is beryllium, which is happy with 4 electrons, and boron, which is happy with 6 electrons. The next exception is that elements in period 3 and after can hold more than 8 valence electrons. So anything sodium and past sodium can hold more than 8 valence electrons. And you'll see instances later in this video where having more than 8 valence electrons can be beneficial to the structure of the molecule. The last exception is that when there's an odd number of electrons in a compound, it's impossible for all of the atoms to have a full octet. So for example, we have nitric oxide here, which has a total of 11 valence electrons because 5 of them come from nitrogen and 6 of them come from oxygen. So we can use guess and check to try to draw in a full octet for nitrogen and oxygen. So if we try to put a double bond, which means that there are 4 electrons in this bond because there are 2 in this and 2 in the second. So all bonds hold 2 electrons. And because oxygen is more electronegative than nitrogen, we can preferentially put the electrons around oxygen. So now this is 8 electrons. And then we put in the 9th, 10th, and 11th, and we can see that nitrogen doesn't have its full octet. And we can draw it in different ways. We can try a triple bond. So that's a total of 6 and 7, 8, 9, 10, 11. So now you can see that nitrogen has exceeded its valency. So nitrogen cannot hold more than 8 valence electrons, so this won't work either. And you can try any different combinations of these, 11 electrons that you want. You are never going to find a way for the octets of both nitrogen and oxygen to be filled with 11 electrons, because with this odd number, it means that one of the electrons will be unpaired. To give a brief overview of the different types of bonding, the first is ionic, which means that one atom gives up electrons to a different atom and then they become their ionic forms. So this is very favorable for sodium and chlorine because sodium only has to lose 1 electron to become its most stable form and chlorine only has to gain 1. So this follows the Octet Rule. So if sodium were to give 1 electron to chlorine, sodium would become sodium plus, which follows the Octet Rule, and chlorine would become chlorine minus, which also follows the Octet Rule. So forming ions is very favorable for these 2 elements. Covalent bonds, on the other hand, are when 2 different atoms come together to form a bond where they share the electrons. So in sodium and chlorine, they're not sharing their electrons. Chlorine has all of the electrons. But in a covalent bond, like in diatomic chlorine, this chlorine only needs 1 more electron to form an octet, and this other chlorine is the same. So if these two electrons come together to form a bond, you can see that the left chlorine has 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8, and the right chlorine has the same. So forming a covalent bond is favorable for these elements. Now, a coordinate covalent bond is similar to a covalent bond where the two elements will share electrons. However, in a coordinate covalent bond, one atom has both the electrons that are forming the bond. So in this case, when we have a hydroxide ion coming together with a hydrogen ion, the hydroxide has both the electrons. So when the hydroxide attacks the hydrogen ion, this will form this bond here. So this bond is coordinate covalent. However, this other bond, we don't know, but this other bond was probably covalent, in which the hydrogen had one of the electrons and the oxygen had the other. So it's not always obvious to tell what bonds are coordinate covalent and which bonds are covalent. You just have to know where the electrons came from. And in this case, these electrons came both from the oxygen, which makes this bond coordinate covalent. Chapter 3.2 goes more into depth about ionic bonds. So as we talked about in the last slide, sodium and chlorine are good examples of a compound that forms ionic bonds when they come together. So chapter 3.2 specifies that a cation and an anion is always formed when an ionic bond forms. So what defines an ionic bond? Like, how do you know when two elements are going to form an ionic bond? So for this, you have to look to electronegativity. So here is a graph of the Pauling electronegativity scale, where every element is assigned a number based off of their electronegativity. And if the difference between the two elements is greater than 1.7, this means that they will form an ionic bond. So sodium, which is 0.9, and chlorine, which is 3, this difference is definitely bigger than 1.7, so they will form an ionic bond. Now, it's not very feasible to memorize this entire scale just for the MCAT. So a good rule to remember is that ionic bonds generally form between metals and nonmetals. So nonmetals tend to have higher electronegativity values, and metals tend to have lower electronegativity values. And this makes sense because nonmetals are on the upper right-hand corner, which have high electronegativity values, and metals generally hold on to their electrons a little bit looser. And metals are more capable of cationic forms. So some characteristics of ionic compounds is that they're soluble in water because they're charged, and charged compounds are generally more hydrophilic and more dissolvable in water, as well as different polar solvents. And ionic compounds generally form a crystalline lattice in their solid form. So you might have seen this NaCl or sodium chloride lattice in your general chemistry classes, and this is very typical of ionic solids. Chapter 3.3 goes more into depth about covalent bonds. So in covalent bonding, it's possible to form single, double, and triple bonds. And this is referred to as the bond order. So a bond order of 1 would mean a single bond, and a bond order of 2 would mean a double bond, which just means the number of bonds that are between two atoms. So bond length refers to the distance between the two atoms in the bond. So bond length is the longest with a single bond, and it's shorter with a double bond, and it's shortest with a triple bond. Because in a single bond, the two atoms are only sharing 2 electrons, so they're connected, but it's weaker than in a double bond where they're sharing 4 electrons, and a triple bond where they're sharing 6 electrons. So when they're sharing 6 electrons, they're being held very closely together, and so the bond length is shorter. And bond energy is the amount of energy that it takes to break a bond between two atoms. So bond energy is highest in a triple bond, which makes sense because if you wanted to break a triple bond, you would have to break 3 entire bonds, which separates 6 electrons. and it's stronger in a double bond than in a single bond. The single bond is the weakest. But it's important to note that the triple bond isn't 3 times as strong as the single bond. The first bond is the strongest, and the second bond is slightly weaker than the first bond. So this means that 3 single bonds are stronger than 1 triple bond. There are 2 types of covalent bonds. One is a nonpolar covalent bond, which is when the difference in electronegativities between the 2 atoms is less than 0.5. And the other is a polar covalent bond, which is when the difference in electronegativities is between 0.5 and 1.7. Now, I don't find this definition particularly helpful because covalent bonds are generally formed between the nonmetals, so between one nonmetal and another nonmetal. And in this type of bonding, you'll very, very, very rarely find 2 atoms that are less than 0.5 electronegativity units from each other. So for example, carbon and nitrogen like to bond with each other pretty frequently, and this difference is 0.5. Now, the bond between carbon and nitrogen is very much polar. This would definitely be considered a polar covalent bond. And so in general, the only nonpolar covalent bonds you'll find are the bonds between 2 heteroatoms. So bonds where the 2 atoms are exactly the same. So when you have chlorine bound to chlorine, this is completely nonpolar because both have the same electronegativity value. And in a polar covalent bond, such as in water, there are 2 ways of designating this polarity. One is with delta plus and delta minus, which means that oxygen is the more electronegative one, so oxygen will, in this bond, pull more of its electrons toward it. So these 2 shared electrons are not shared equally, more of them are pulled toward the oxygen. So hydrogen has a partial positive and oxygen has a partial negative. And another way of designating this is with this arrow, which means that this side is positive and this side is negative, and both of these mean the same thing. Another type of covalent bond is a coordinate covalent bond, which we talked about earlier, and this means that both of the electrons used in this covalent bond come from one of the atoms. So in this case, nitrogen is giving both its atoms to boron, which forms a coordinate covalent bond here. And nitrogen, because of some properties of nitrogen that will be talked about later in the series, nitrogen likes to form coordinate covalent bonds, and nitrogen is quite happy with a positive charge. And so when you see a bond between nitrogen and something else, a lot of the times it will be a coordinate covalent bond, especially when nitrogen is positive. Lewis structures can be a helpful way of drawing out a molecule to keep track of the bonding versus the non-bonding electrons. So the bonding electrons are electrons shared between 2 different atoms, and the non-bonding electrons are also known as lone pairs because they're off on their own and they're not bonding with anything. So a good rule that I like to keep in mind is the HONC rule. And in drawing Lewis structures, what this means is that hydrogen likes to form one bond because it has this one electron to form the bond, and it has a need for one other electron. So when it forms one bond, it's perfectly happy. And oxygen likes to form 2 bonds because oxygen has 2, lone electrons, and if it got 2 more electrons, it would be happy. And nitrogen similarly has 3 extra spots for electrons, and carbon has 4. And this is why carbon is such a common element in our biology and in the world as a whole, because carbon can form so many bonds with different things, and it can form so many diverse structures. And what the HONC rule means is that carbon is most likely to be at the center of a Lewis structure, carbon and all of the other elements in its group. And nitrogen is second most likely, oxygen is third most likely, and hydrogen is least likely. You'll almost never see hydrogen or any other of the group 1 elements as the center of a Lewis structure because it can only form one bond. So if it's in the center, there can only be one bond out of the center. And so, for example, here I have HCN, and we're going to draw the Lewis structure of this. So following the HONC rule, the carbon should be at the center of this molecule. And hydrogen is on one side and nitrogen is on the other side, and it doesn't really matter which side either of them are on. So then we count the valence electrons in each atom. So carbon has 4 valence electrons, nitrogen has 5, and hydrogen has 1. So this makes 10 valence electrons total. And so we're going to try to fill this in to fit the octet rule as best as possible. So we know that hydrogen can only make one bond because hydrogen is happy with 2 electrons. And these 2 electrons that are shared count both in the 2 electrons that hydrogen wants. So now carbon wants 8 electrons, and so does nitrogen. And because we've used up 2 electrons in this bond to hydrogen, we only have 8 electrons left, or we have 4 bonds left that we can make. So the only way to satisfy this valency is if we put a triple bond between carbon and nitrogen and a lone pair on nitrogen. And so with this, carbon has its 8 electrons, 6 here and 2 here. Hydrogen has its 2 here, and nitrogen has its 8, 6 which are here and 2 which are here. And so this Lewis structure satisfies all the rules of valency. The next example is sulfur dioxide, and it can be kind of hard to decide which atom is the central atom in sulfur dioxide, because the HONC rule can also be known as the 1, 2, 3, 4 rule, which means that hydrogen forms 1 bond, oxygen forms 2, and so on. And sulfur is in the same group as oxygen, which means it also forms 2 bonds, or it likes to form 2 bonds. And therefore, sulfur might be given the same priority as oxygen. However, there's an implicit rule in drawing Lewis structures that they should be as symmetrical as possible. So following this, we put sulfur in the middle of this Lewis structure, and we put the 2 oxygens on the side. And so we can try to fill this in knowing the number of valence electrons they have. So sulfur and oxygen both have 6 valence electrons. So we do 6 times 3 equals 18. There's 18 total valence electrons in this molecule. So in this interest of symmetry, and knowing that sulfur can have an expanded octet, which means that sulfur can have more than 8 valence electrons because sulfur is group 3 or beyond, we could try to put 2 double bonds between sulfur and oxygen. And we can try it like this. And if I'm going a little bit too fast, feel free to pause and look and try to think through yourself about why this makes sense. So oxygen here has 8 valence electrons because 1, 2, 3, 4, 5, 6, 7, 8, and so does this right oxygen here. And the sulfur, while it has an expanded octet, it doesn't necessarily violate any of the rules we've said before. But you can also draw other structures of sulfur that also make sense. For example, you can put a single bond and a double bond this way, and this also adds up to 18 electrons. But you can draw one more, which, while this last one is the mirror image of the one before it, this one is definitely a different structure. So although these two are mirror images and they might seem alike, this oxygen is not the same oxygen as this oxygen. And so these two are 2 different Lewis structures. So how do we decide between these 3 very possible structures which one is the best? So we can use this concept called formal charge. And formal charge is calculated for each individual atom. So the formal charge is V, which stands for the number of valence electrons in its elemental form. So for the elemental form of sulfur and for oxygen, this is 6. And this is subtracted by the number of non-bonding electrons. No, that's not how you spell non-bonding. Okay, this is subtracted by the number of non-bonding electrons, and this is subtracted by the number of bonds. So to see this in action, we can calculate it for every single atom in this form of sulfur dioxide. So in this oxygen, the number of valence electrons in its elemental form is 6. The number of non-bonding electrons is 1, 2, 3, and 4. So this is -4. And the number of bonds it has, which is 2 bonds. So -2. So the formal charge of this oxygen is 0. And we can calculate it for the sulfur as well. V is 6, non-bonding electrons is 2, and number of bonds is 4. So the formal charge of the sulfur is likewise 0. And the formal charge of this oxygen is also 0 for the same reasons that the left oxygen was 0. So all 3 formal charges in this structure of sulfur dioxide is 0. For the next structure, the left oxygen has a V of 6 minus the number of non-bonding electrons, which is also 6, minus the number of bonds, which is 1. So this oxygen has a formal charge of -1. And this sulfur has a V of 6 minus the number of non-bonding electrons, which is 2, minus the number of bonds, which is 3. So the central sulfur has a formal charge of +1, and the right oxygen has a V of 6 minus number of non-bonding electrons, which is 4, minus number of bonds, which is 2. So this right oxygen is neutral in terms of formal charge. And on the structure on the very right, we can assign the same but symmetrical formal charges. And so this video is getting kind of long, so I'm going to make a part 2 of it. And so look out for part 2 to see what these formal charges mean in terms of which structure is the best. And spoiler, it's this one, because even though it violates the octet rule, all 3 of these formal charges are 0, which is much better than if you had formal charges. Thank you so much for watching. I'm so sorry that this chapter has to be spread into more than one video, but the next one is coming soon. Thank you so much for watching.